Okay. Any questions regarding final exam? Oh, yeah, I forgot to mention the expected, the median, okay, will be around 70 points. That's my estimate. So if you find, okay, you have 20 to 30 points that you don't know how to do, that's perfectly fine, and don't panic. And then the final score will be curved if you choose letter score. The median would be A minus. Okay. Now, today we're going to talk about interesting topic, and then also something that widely used in quantum communication. It's called quantum teleportation. And then before we dig into what is quantum teleportation, I want to briefly mention what is teleportation, right? The definition. Teleportation has been actually you probably have seen it in a lot of movies. Okay, the teleportation, the definition is that you can transfer some stuff, you can think about it as matter or energy, okay, without actually transferring without transferring them in physical space. Okay, for example, if you have a cell phone or you have something in A, and then you want to give it to B, okay, normally you would just use UPS or FedEx, and then physically it will move from A to B. Okay, that's called transfer, right? Just transportation, not teleportation. Teleportation means that you destroy this. Well, not destroy. The particle, the matter at A, okay, disappear, and then reappear in B. Okay, this is called teleportation. It's like you can't see it physically move from A to B, but then it disappear in A and reappear in B. Okay, that's teleportation. It's a dream that ultimate dream for travelers, right? It's just like immediately you move from place A to place B, and then you guys know what to do if this technology ever being invented, right? You should short all the stocks of aircraft companies, and then all the airline companies. Okay, and so apparently, okay, teleportation, the conventional definition teleportation, nowadays still haven't been invented, but then it's only in movies. But there's a different version of it. It's called quantum teleportation. Okay, quantum teleportation, and actually work in a very interesting way. But then people use it to transfer information. Okay, with 100% security, right? You can eavesdrop this teleportation. Okay, the idea is that suppose you have a particle in A, quantum particle in A. For example, you can have an atom, or you can simply have a qubit, right? And then Alice, let's call it Alice. Okay, Alice have a qubit, and then the qubit state is psi A. Just very simple, a very simple general one qubit state, right, in superposition between 0 and 1. And then what quantum teleportation means is that you can transfer, okay, if you look at this qubit, the important information about this qubit is alpha and beta, right? It's alpha and beta. So what quantum teleportation means is that without physically transporting this qubit, okay, but somehow, okay, without transferring this, but somehow, let's call it C, okay, Chess. This is Alice. Okay, Chess is able to receive, or is able to recreate a qubit that's exactly the same as Alice qubit. Okay, and then from quantum non-cloning law, okay, or theorem, you know that when this happens, Alice qubit will be destroyed. Okay, it will be mapped to other state. Okay, because you can't duplicate a unknown qubit. Okay, and let me say this. Okay, you guys might think, oh, is it what happened is that Alice just sent out alpha and beta, the two numbers to Chess, so that Chess actually can recreate a state like this. No, right? That's not teleportation. That's just sending classical information. What really happened, okay, in the definition of quantum teleportation is that when Alice can send some information to Chess, but that information is not enough to recreate or to guess what alpha and beta is, right? So Alice sends some information here, but then that information is not related to alpha and beta. But then Chess is able to get a state exactly the same as Alice, and the Alice state will be destroyed. Okay, so it's like a less fancy version of teleportation. Okay, what's being teleported here is the information Alice have in his qubit. Okay, it's not the physical particle that carry the information being teleported. It's the state of the particle being teleported. So and this might be very helpful if you think about it. This type of teleportation is that this idea might be a little bit scary and can give you a nightmare. But if you think about it, is that I'm not sure if I get this idea from a movie or something, but I think it's that if some people imagine that you can make a duplicate of yourself, like cloning, okay, and then frozen it somewhere. And then, for example, if you want to travel to Hawaii, okay, you just ship that copy to Hawaii, and then you transfer all your information, all your memories in your mind to that copy, and then reactivate that copy, and then deactivate you. Okay, then you kind of transport yourself to that place, but you require two physical copy of the particle itself. Okay, so it's the same idea. And let me. Any questions about the definition of quantum teleportation? Okay, so let me explain a little bit why quantum teleportation is something worth discussing, right? So one idea, okay, one thought is that you guys might wonder, okay, why not Alice? Why not just send the particle? Okay, why not just send a qubit from Alice to Chess? Okay. Well, there are two thoughts here. One is that sending the qubit in a channel might not be secure, right? Because it can be get by another party, okay, by someone airdropping here. And the second thought is some quantum information, for example, if it's inside a superconducting quantum computer, okay, you cannot easily transport it from from A to C. Right, because like if you bring it to room temperature, and then the thermal decoherence actually destroy that state. So a lot of times that teleportation, can be really handy in information communication. And the quantum teleportation concept was proposed in 1993. Okay, it was established to allow the state, okay, to be transferred between Alice and Chess, and then the actual experiment that first fully demonstrated quantum teleportation was in 2001 in University of Maryland, and then a recent advance was I think in 2017 or 2018 that the Jianwei Pan's group in China actually did a teleportation between the ground and then the satellite, which is kind of revolutionary because in the past, I think it's very difficult to get over a few hundred miles. And now with the satellite, you can actually get the teleportation from between two continents. Well, European and Asia are technically in the same continent. Okay. Now let's talk about how you can make the quantum teleportation work. And the basic idea is the same from the previous lecture. In the previous lecture, what we learned is that if you have two particles, okay, let's say A and B, they are in entanglement state, right? They're in entanglement state. Then if you measure A, okay, if you do a measurement on A, that will actually change B. Okay, that would change B. So now the thought here would be, okay, Alice now have the qubit has the information. If there's a special relationship between the qubit held by Alice and Chess, can we do a measurement on A, on the qubit of Alice, and then the information is teleported to Chess, right? So that's the very basic idea that can you use entanglement, okay, to transfer information? And the answer is yes, but then of course the schematic is a little bit tricky. That's why it took people many years to figure out this. And then I will try to make this clear. Well, I will try to make this schematic clear, okay, in the next probably hour. Okay, now let's look at how you can do teleportation. So the initial setup is that, well, if you're Alice, okay, it's the same as here. You hold a state that has the quantum information, and then you want to send it to Chess, okay. And the first step you need to do is to invite a friend called Bob, okay, into this game. Bob here. And then what Bob needs to do is that Bob Bob has two Bob has two qubits, and then these two qubits are in maximum entanglement state. For example, Bob's qubit can be in, okay, this is a typical entanglement state we have talked about, right? So Bob prepared two qubits, that's the entanglement state. And then what Bob did in the third step is that he sent one of the qubits to Alice, and then the other qubit to Chess. Okay, so now Alice has two qubits, Chess has one qubit. Okay, Chess has one qubit. Now you can see here now, so because Bob's two qubits are entanglement, right? So they're in a quantum correlation. So in a way, right, this qubit here, okay, let's call it, let's see. Yeah, I think the label here is this particle is A, this is B, this is C, okay? So there's a quantum correlation between B and C, okay, while the information right now is loaded in A, right, loaded on A. So we need to figure out a way that when Alice do something to A and B, okay, this information on A can be transferred onto C, okay, transfer onto C. And you can think about, okay, what you need to do here, right? First of all, based on previous understanding of entanglement, how entanglement works, right? If you make a measurement on one particle, it will change the other particle. So you need to do some measurement on B, okay? Then that measurement result would change the state in C, okay? But then right now B doesn't have any information on it. Right, the information is on A. So there are two possible thoughts is that maybe, okay, you can use, let's see, option 1. Maybe you can apply a gate between A and B, okay, so that you actually load the information from A to B and then do a measurement on B. Okay, and then option two is that because you know that A has the information, but then you also need to measure B, okay, can we do, let's see if I can say this in a very precise way. So the idea is, okay, can we do a measurement, a collective measurement on A and B at the same time. Okay, so we measure A and B in a very special way, so that when you measure A and B together at the same time, the information on A can pass to C, okay, through B. Okay, that's the basic idea. And then, at the end of this class, we'll prove that these two are equivalent. Yeah, if you can do B, if you can do option 2, you can do option 1. And then, by the time, people didn't know that. I think the historically, okay, option 2 was first proposed and also first demonstrated, and later people realized that these two are kind of the same thing. And then if you can do one, you can apply the other. Okay, and so let's continue with this option 2 here and see what exactly you need to do to teleport the information. Okay, what you do is that Alice, perform a measurement. I use M to represent it. Perform a measurement on Bell state basis. On A and B. Okay, this is a special measurement. Special measurement, collective measurement on A and B at the same time. Later we'll take a look at what Bell state is and then what this measurement is. And then after measurement, Alice will get 4 different results, because you can think of it as that if you measure A, right, 0, 1, measure B, it will also be either 0 or 1. Right? So in total, there will always be 4 possible results, regardless of what basis you choose, so that Alice will get 4 different results, 4 possible results. And then Alice will send this result via a classical channel. Okay, send the measurement result via classical channel to chess. Okay, in this process, the information is about the measurement result, not about the state, right? So you're not leaking any information. And then the final step is that chess perform a single qubit, single qubit gate. Okay, on C, based on the this information Alice sent him, or based on Alice's measurement result. Okay, and this is the framework of this schematic. And then, right now, okay, if you just look at it, of course, you won't understand what it is, right? Because there's so many new stuff here. And then, let's go through this step by step, and then show you guys, okay, how this measurement, how this schematic actually works, and how you can transfer, or when the information is really transferred. Now, the first thing that we need to take a look, okay, is that after Bob, okay, generate this entanglement particles and then send one to Alice, one to Chess, what are the state look like? What does the state look like? Quantum state look like, right? So the quantum state look like you have particle A. Okay, and then you have this entanglement state, right? okay? You have this entanglement state. And now when you pass a particle to Alice and then the particle to Chas, it doesn't change the state, right? It doesn't change the state. But then writing the state in this way doesn't really help you to understand how the measurement is being done, right? Because if you take a look, right, A and B are now at the hand of Alice and particle C is at the hand of Chas. But when we write it down like this, it looks like, okay, particle B and C are together and then particle A are alone, right? So we want to rewrite this in a very simple way, is that you do this, you take this direct product and then put it in between. Well, let me put it this way. You first, okay, you just do the expansion, okay. You do the expansion, you will have 1 over square root of 2, and then alpha 0, 0, 0, okay. And then alpha 0, 1, 1, and then beta 1, 0, 0, and then beta 1, 1, 1. Okay, and then if you write it down, if you want to write it down as quantum state of A and B, and then direct product with quantum state C, okay, then what you need to do is that you need to put state 3, right? There are two options. One is 0, the other is 1. You want to write it down as you want to collect the common term in the front. Then what you will have is that you will have 1 over square root of 2 alpha 0, 0 plus beta 1, 0, okay, direct product of 0 plus, and then now you have alpha and then this, okay, so alpha 0, 1, okay, plus beta 1, 1, product with 1. Yes, okay. So now you can see that, okay, these two states are the same state, okay, are the same state. What I do is simply rearrange them, right? I write particle A and B together and then direct product with particle C. Okay, here again, particle A and B, write them together, direct with C. Okay, so this way, it makes it a little bit clear of what the state Alice have, okay, these two possible states, and then what state Chas have, right, here. Any questions here so far? Okay, now let's take a look of what type of measurement we need to do, okay, in order to transfer the information from A to C. First of all, if you just measure particle A on its 0 and 1 basis, okay, you can see that it will not change the state of particle B and C at all, right? Whatever you do with A has nothing to do with B and C, which makes sense because B and C have entanglement. A has nothing to do with B and C, right? And then if you take a look, and then if you say, okay, what if I measure particle B, right? If you measure particle B and then you get 0, then particle C will be 0. If you measure particle B and get 1, the result will also be 1 for particle C, right? And then the information on A will not transfer to C, right? This is understandable because A is not entangled with B or C at all. Right, B and C, they're entangled but has no relationship with A. So from here you can see that, okay, in order to transfer information from A to C, you need to do something with A and B together. Right, you need to measure them on a common basis of A and B, or you do a gate, okay, to to transfer information from A to B. And and in 1993, okay, people find out that there's a type of measurement you can do to actually transfer this information. And then that measurement nowadays are called a Bell measurement. And then I will go I will explain a little bit what Bell state are, and then what we mean by Bell measurement, Bell state measurement. So before, okay, we say that, well, you can entangle two particles, and then one of the entanglement is like this, right? Particle A is 0, then particle B will be 0. Particle B is 0, particle C will be 0. Particle B is 1, particle C will be 1. But there's other possible entanglement state as well. And then the four very famous one are defined by Bell. Okay, it's called Bell basis. Let me show you what it is. The first basis is the same as the one that you often see, and then the second one is very similar, but okay, with a minus sign here. And then there's third state is the opposite entanglement, right? When particle when particle B is 0, particle C is 1, particle B is 1, particle C is 0. It's the opposite type of entanglement. And then the final one is same as previous one, but then with a phase difference. Okay, and then you can check that you can check that these four states, they're actually orthogonal to each other, right? It's very clear. These two are orthogonal, right? This times this will get you 1, but this times this will get you minus 1. Also, these two are orthogonal to each other. And then you can also see the note, I think, in page 5. Yes, in page 5, the note actually shows you these two and these two are orthogonal. So all of them are orthogonal to each other. And then the second thing, other than orthogonal, is that these four states actually can be used as a basis for your system. What we mean by basis is that it's similar to your coordinates, right? X, Y, Z. That describe that you use to describe a vector. There's more than one way to set up X, Y, Z, right? You can rotate it, you can move it, and these coordinates are equivalent to each other as long as this, the basis X, Y, Z. First of all, they are orthogonal to each other, which I briefly explained they are, and second is that they are complete. Meaning that using X, Y, Z, okay, you can describe any vectors or any particle, any positions in your space. And then when you look at here, okay, Bell state, what it's used for is to describe, what it's used for is that you have two particles, right? And then for two particles, your original state basis is 0, 0, 0, 1. 1, 0, and 1, 1, right? If you're given 2 qubit, and then the basis usually you will choose is this basis, right? It's just the binary, right? 0, 0, 1, 1 all the way. And then what you can find is that, okay, the Bell states can also be a basis because Bell state is also complete, right? If you take a look, is that when we say these four are bases, what we mean is that any quantum state of the two qubit system can be described as a superposition of all of these four bases. And then the Bell state, okay, the reason we say it's complete is because you can express the four bases of your qubits, two qubit system, in superposition of the Bell bases, right? It's very clear. You can see that if you add these two together, you can cancel 1, 1 here, and then there's 1 over 2 of 1 over 2, so that you divide down by 1 over 2. And then you can have 1, 1, same, just with a minus sign. Okay, and then 1, 0. And then 1, 0. Okay, so what it means is that you can use Bell bases and their linear superposition to express the original four bases of your two qubit system. So therefore, because these four bases is good enough to describe to describe all the states for your two qubit system, then therefore, okay, the Bell states are also good enough to express all possible state for your two qubit system, right? So this four Bell state satisfy the criteria for a basis, right? First, they're orthogonal to each other. Second, they're complete. They can describe any states. You can use their superposition to describe any states in the two qubit system. Okay, and then if you look at this the Bell basis, the major difference between the Bell basis and then the regular basis is that the regular basis is just, they don't really have entanglement, right? It's just 0, 0. It's just 0, 0, right? It's a state. Here, the Bell basis, all four of them are entanglement states, right? This one very clear. This one is also just a phase difference, and then this is also clearly entanglement state, right? 0. The first particle is 0, second qubit is 1, first qubit is 1, second qubit is 0. This is minus sign. Okay, so the Bell basis is special in a sense is that the basis itself, okay, are all maximum entangled. Any questions here? Do you guys actually know what I'm talking about? Okay. So now, let's look at this, critical steps of how the teleportation is done, right? So, described by the previous protocol, okay, what we mean, the step, okay, after following, okay, distributing of these two entangled particles to Alice and Chess, is that Alice, okay, will take these two qubits and then do a measurement on Bell basis, okay, Bell basis measurement, meaning that Alice is not interested in knowing whether they are in 0001 or 1011. She's not interested in this. What she's interested in is that she wants to know whether these two particles are in which type of entanglement state, right? There are 4 different bases for Bell bases, and then they are all entanglement state. What type of entanglement state Alice 2 qubit is in? And you might wonder, okay, but A and B doesn't really have entanglement. But it doesn't matter, right? As long as you have a basis, and then you can design your measurement setup to measure on that basis, then you can get some result. Okay, it doesn't matter. Previously, you're not in this basis. It doesn't matter. Okay, A and B doesn't have entanglement. So the way that you can kind of understand this is that you can is that when you choose a basis in quantum mechanics, we know that from the postulate is that when you choose a basis, when you try to measure something, right, and then your measurement result will always be the eigenstates or the eigenvalue, and then your state will collapse into eigenstate. And what we're trying to do here, the Bell measurement, is that you're measuring something, and then the eigenstate of what you measured are only these 4 states, right? So regardless of what your initial state is, after the measurement, it will be projected into one of these 2 states, right? So these are you can think of these are the eigenstates of an operator, and then you measure the value of that operator, okay? Now, how to do that measurement physically is actually a very difficult question, but we can first assume that we can do Bell state measurement. Then how can we express it mathematically, right? So the easiest way to do this, okay, is that we already write it down 0011, 0110. We already write it down here. We just replace them, okay, insert them into here, and then to replace the previous basis with the new basis, right? Very simple. And if you do that, then what you will see is that the state become, just insert this into here, okay, the state become 1/2. Let me just write down the final answer, and then you guys can check if you guys want to know the middle, well, let me write it down here, okay. So the first one is alpha, okay, alpha first Bell state, and then cross product with 0, and then alpha again, right? This one has second part, Bell state minus cross product again with 0, and then you do the second one is beta, right? Okay, and then 10 is here. Okay, cross product with 0, and then minus beta, okay, cross product with 0. So this is, this is this first state, first part, and then now you move on to the second part. You have alpha, 01 is here, okay, so alpha plus cross product with 1, and then plus alpha minus 1, and then finally you have beta 111, right? This state. So beta 11 is psi plus minus psi minus. okay, minus beta okay. So it's just simply substituting this into there, and then you can see that because the measurement is done on particle A and B, right, on Bell state, so you want to collect the term that are the same and you put them together. So first one is this, and then you have that. Let's see, here's and then psi plus, and then psi minus. Okay. Okay, and then if you put these terms, common terms together, then what you will get, okay, what you will get is that right, this term, and then it's alpha 0 plus beta 1. Okay, and then alpha minus, well, and then minus, you have alpha 0 minus beta 1. Okay, and then for psi plus, okay, if you have beta 0, and then beta 0 plus alpha 1. Okay, and then finally you have psi minus term. Psi minus term here, there's one. Here there's another. Okay, so alpha 1 minus, yes, minus beta 1, beta 2, sorry, beta 0. Okay, so these are the 4 possible states, okay, after you rewrite particle A and B into Bell basis. So far, we didn't do anything, okay, we simply write it down, write A and B in Bell basis so that we can predict if we want to do a Bell basis measurement. If we want to measure A and B on Bell basis, what are the possible results we can get? And you can see this coefficient here, 1/2, okay, and then square of that would be the probability, right? So you have this 4 state, okay, and then their probability is, well, their coefficient in the front is all 1/2, right? So what that means is that when you do a Bell basis measurement, okay, you have 25% on this state and also that state, this state, and that state, right? So when you do a Bell basis measurement, it's 25% on, one of those states. And the interesting part, if you notice, okay, if you just notice what the state has become, right? This, the part in the front is A and B, right? It's particle A, particle B. And the one on here, on this side, is C, particle C, right? You see that it's very interesting, okay, if your measurement result on the Bell basis return with the first Bell state, then your particle C automatically become the state that Alice originally have, right? Alpha 0 plus beta 1, okay? If your measurement result is is the second Bell state, okay, phi minus, then you still get the information of alpha and beta, but then you just have a minus sign here, which is easy to correct, right? By doing a phase gate. Yeah. And then if your measurement is per psi plus, then you still get alpha and beta, but then their coefficient is flipped, right, from the original information. So what you do, okay, what you need to do is that you need to apply an X gate, right, NOT gate, right, to change 0 from 1 and 1 from 0. And then your information will, your state will again be the same as the state Alice had. And here is just a combination of these two, right? You need the X gate, and then also you need a NOT gate, right? You also need a phase gate to change minus from plus. So here, from here, what we already can see is that by doing a collective measurement on A and B, okay, on the Bell basis, on the entanglement basis, it's possible to map the state Alice originally have to chess. Okay, and then remember, when you do this measurement, you're not sending anything physical from Alice to chess. The reason that this state chess has, becomes something like Alice state is because the particle B and particle C, they have a quantum, entanglement, or they have quantum correlation. Okay, so now let's describe the final, steps that you need to do to complete this quantum teleportation. So when Alice do the measurement, he has 25% probability of getting phi plus state, right? Phi plus state, and the state this is Alice result. This is chess qubit. Okay, if Alice measurement result is this, is phi plus, then chess, and this is probability, chess state is 0. Right? So in this case, chess didn't have to do anything. Chess already get the state Alice want to send him. Okay? And there are 25% chance that Alice will measure phi minus state. And this, in this case, okay, the qubit chess have is alpha 0 minus beta 1. Okay, and let me just finish all this. Because we have kind of explained this already. Okay, now the question is, if you look at this, you will say, oh, well, it's not a very good teleportation line. It's because only 25% of the time, okay, chess qubit has the correct information of Alice qubit, right? Only 25% of the time. But if you really look at it, these are not far from being correct, right? These are just there's plus minus sign difference. These are just a gate NOT gate difference. These are the combination of these two. So if you want to make this quantum teleportation work 100% correct, then what you need, okay, this is why we need this classical channel, is that Alice tell chess what her measurement result is, right? There's 1 over this 4, right? So if Alice measure phi plus, then chess, okay, it does nothing, right? Identity operator. Chess doesn't have to do anything because he already has the state. If Alice measure this, then he would tell chess, okay, I get this state, and then what chess would do, okay, chess would do a Z gate, which we know is 0, which we know Z gate is Pauli Z gate 1, 0, 0, minus 1. right? It changed minus beta to beta, and then okay, and then if you measure psi plus, okay, Alice tell Chaz, okay, I might measure this, and then what Chaz would do is do an X gate, okay, which will flip 0 and 1, and then finally, if the measurement result is phi minus, then what you do, what Chaz need to do is to first apply an X gate, okay. When you do an X gate, you change from this state to that state, and then followed by a Z gate, okay, followed by a Z gate. And this way, after this operation, Chaz qubit will guarantee to be the same as Alice's original qubit, okay. And this, by doing this, you complete the quantum teleportation. And I want to briefly, this is just a protocol. I want to briefly explain what really happened in this teleportation process. Okay. First of all, the question you might ask is, when does the transfer of information happen? Okay. The transfer of information happened when, well, in two steps. The first step is when Alice did this Bell state measurement, right? Bell state measurement. When you measure B, okay, when you measure B, and because B is entangled with C, right? So their quantum correlation, okay, is now in fact that transfer part of the information of A to C. Okay, you can see that after the measurement, Chaz qubit already have the information of alpha and beta, but then there's just a ambiguity, okay, of which one is alpha, which one is beta, okay, on 1 and 0. Also, there's a 180-degree phase ambiguity, right? And the second step, that to eliminate this ambiguity, is using this classical channel, right, to tell Alice measurement result to Chaz, and this way, okay, you can eliminate this ambiguity by operating a gate, okay, operating a gate on Chaz, by Chaz. And then the second part is that so that this information transfer is really two-part. And you can see here is that because you need classical channel, okay, to finish this transfer information, so that this transfer of information actually does not violate, cannot be faster than speed of light, right? So when you do this measurement, Bell state measurement, although it looks like the information has already been transferred to here, but now think about this, is that you have because of this ambiguity, actually there's no way that you can actually use this data. Okay, so you need this classical channel to complete this transfer of information, and then classical channel is the speed of classical channel, of course, is limited by the speed of light, so that this quantum teleportation does not violate the special relativity, saying that no information can flow at a speed faster than light. Okay, and the second thing is that is this teleportation, okay, sending information from Alice to Chaz 100% safe. Okay, if you think about it, then well, in a way, yes, because the only thing that you can possibly eardrop is the classical channel, and the classical channel actually doesn't have any information about alpha and beta, right? Classical information only have, tell you the result of one of these four states, right? So it's 0, 0, 0, 1, 1, 0, 1, 1, right? You can use the binary, 2-bit binary information to represent that, and has nothing to do with alpha and beta, because alpha and beta can be, a very long string, right? It can be, for example, 0.5567, right? You can have a lot of digits in it, okay? So if dropping the classical channel actually doesn't work, okay? And second part you can think of is that, well, then is there any other channel we can eavesdrop, right? It's very unlikely, because if you think about it, how the information transfer is complete, right? The first step is complete by doing the measurement on Alice A and B, okay, and then the transfer information is complete by this quantum correlation or entanglement, right? So, it depends on the correlation. So no information is really, well, there's no physical information flowing from AB to C, right? So there's no way to collect that quantum correlation if you're someone trying to eavesdropping the system. The only possible way, okay, the only possible way is that you can stop here. Is that when Bob send a particle to Chess, okay, you can take that particle. Let's say if you Eva, you can take that particle, and then you can substitute that with another particle, send it to Chess. Okay, send it to Chess. It's doable because it's doable because when Chess receives this particle, he's not going to do anything on it because as long as he measure it, Chess will destroy the entanglement here. Okay, but then this way, okay, but then when you're doing this, it's actually quite easy for Alice and Chess to know. Okay, because the reason is that Alice and Chess can use a few testing qubits, okay, a testing information to see that whether their communication channel is working properly. For example, they can set alpha and beta into some well-known state. For example, you can set alpha equal to beta equal to 1/2, right? And then when you do that, Alice, okay, can prepare the state in this way, and then do this measurement, and then Chess will receive that state. And what Chess can do is that Chess can verify whether the state he received is the same state as Alice prepared, right? He can do that. And the only way that the state are exactly the same is when the qubit Chess has a correlation with the qubit Alice has, right? So when Eva actually do this swap or do this, steal this qubit and send an unentangled qubit, then the qubit Chess actually has no relationship with this qubit. So what Chess will measure is a random number, okay? It's some random state, and then this way Alice and Chess will be able to know that someone is eavesdropping them, and then can abandon this channel, okay? And then once again, similar to the idea of quantum key distribution, the quantum teleportation is 100% secure in a sense that if someone is eavesdropping you, you can know, right? It doesn't mean that it's 100% effective, which means that nobody can, it doesn't mean that nobody can stop you from communication, stop your communication, right? Because very easily you can, very easily the other party can just cut your classical line, or can just stop entangled particles to transfer from one place to another place. That way you can stop the information transfer. So it's 100% safe, but then it doesn't mean that it's 100% effective, right? If you want to stop people from doing quantum teleportation, it's relatively easy. And but in a way it's similar for other type of communication, right? If in the old days, when telephone has lines, right, you can just cut the line, and then people will lose connection. Okay, any questions here so far? By the way, I really encourage you guys to ask questions, because I don't think all of you understand what I'm saying here, and then this actually will be in the final exam. And if you guys don't have questions, I can move on to some final comments. No questions? Okay, so some final comments. We have 10 more minutes. Is that okay? So now, if you look at the quantum teleportation, the key is, or the most difficult part, other than creating entanglement in some in some situation is actually difficult, is how you can measure the Bell state. Right? How you can measure the Bell state. Bell state are entanglement state. For example, you can measure particle A first and then particle B, right? Because that way, if you measure particle A, and then because of entanglement, it already collapsed into one of the state, right? So the regular measurement method, measure one and another, actually doesn't work. And then so the quantum teleportation method was proposed in 1993, and then the first full demonstration of it was only possible when people realized how to actually make this Bell state measurement. And then it's in 2001, so it actually took people 8 years to figure out the way to do this. And then the actual Bell state measurement itself is very complicated. I'm not going to go over here. But then the key concept there is that if you want to measure A and B, the two particles in an entanglement state or in a collective way, you have to let particle A and B interact with each other, right? So it's very simple, right? If you want to transfer information from A to B and then B to C, you have to create some connection between A and B, and then the best way to do that is by letting them interact with each other. And then mathematically, people can actually prove that. Okay, you need A and B to have nonlinear interaction, not linear, but nonlinear interaction to finish this Bell state measurement. And because that concept is relatively complicated, I want to show you an alternative way that people later also realized that can finish this Bell state measurement and actually have a quite deep, the connection, okay, between, and this actually reveal a deep connection between quantum information and quantum computing. Okay, so now let's consider these circuits. Okay, I think you guys all remember the circuits that, either we discussed in class or we have shown it in the, I think we discussed this when we introduced C-NOT gate, control NOT gate. Okay, at the time that we say that, okay, if you want to create entanglement state, you can actually use this circuit, right? So the first qubit goes through, first of all, at the input port, they all prepare a ground state, and then after the first Hammer gate, right, the first qubit become in a superposition state, right? And then now you go over the C-NOT gate, right? If it's 0, it would do nothing. Okay, so the first state is 0, 0, and then if it's 1, then it would do a X gate, right? Change 0 from 1, right? So the second state is this. Okay, or another way you write it down as. Okay, so this is a very straightforward way to use quantum circuits to create entanglement. Okay, and now you can kind of see that. Okay, when we discuss entanglement, we say that you need particle A and particle B and particle C to interact with each other and then create entanglement. Here, it seems that at first you might think, okay, it seems that these two qubits did not interact with each other, and then we created entanglement. But that's actually wrong, because to demonstrate control NOT gate, okay, in this way in the quantum circuits, what it actually means is that the control NOT gate in the implantation, okay, inside actually A and B has to interact. For example, otherwise, how can the state of the qubit 1 change the state of qubit 2, right? You cannot do that unless you have interaction. Now let's take a look of how we can reverse this and then to do a Bell state measurement. Now if we reverse this circuit, okay, let's say we have input on this side And then first we go over a C0 gate. And then we go over hammer gate. Okay. Now consider if the input state is the first bell state, phi plus. Then after the first, phi plus. Then, what will happen at the C0 gate is that, okay, the first qubit is 0, so you do nothing on the second qubit, so that's fine. And then if the first qubit is 1, then you have to apply a NOT gate, okay, on 1, right? So after C0 gate, this becomes 0, 0, plus 1, 0. And you can see that this is no longer entanglement state, right? Because the second qubit is always 0, so that you go like this. Right? And now you go through a hammer gate. And then we know that hammer gate is a reverse gate. Okay, if you input 0, it will give you a superposition state. If you input a superposition state, it will reverse to the to 0, right? So this one eventually, okay, after the hammer gate will give you a 0, 0. Okay, so it's very interesting now that your bell state after these circuits will give you a deterministic measurement result, right? It's 0, 0 if you measure the qubit on 0, 1 basis. And then you can run the same calculation for phi minus, okay, going through this circuit. And this one, it would be 1. Be 1, 0. Okay, this is understandable because there's a minus sign. This minus sign will carry out to here. And then after hammer gate, it will become 1. And then you can also calculate per psi plus. And then after the circuits, it will become 0, 1. And then per psi minus after this stage will become 1, 1. Okay, so the way that you can actually do bell measurement, people later realize, is that if you can realize control NOT gate, then you can simply run through these circuits, okay, and then measure the 2 qubit. After the circuit, measure the 2 qubit in a normal basis, 0 and 1 basis. Okay, if the measurement result is 0, 0, the first bell state, 1, 0, the second bell state, 0, 1. Okay, third bell state, and then 1, 1, the final bell state. So from there, okay, people actually start to realize or start to figure out that quantum information, okay, through teleportation is equivalent. Well, let me rephrase that. Whether you can do quantum teleportation, okay, rely on whether you can do bell state measurement. Okay, that's people's understanding. And then the second understanding is that whether you can do quantum computing rely on whether you can do control NOT gate, right? Because control NOT gate is a universal gate. If you can do that, then you can do quantum computing. Now, because of this circuit and then this measurement result, you can actually combine these two. Is that if you are able to do quantum computing, right? You have a control NOT gate. In principle, you can also do quantum teleportation because you can use control NOT gate to do a bell state measurement. And the reverse is actually also true, but then we don't have time to prove it here. If you can do a bell state measurement, okay, if you can do a bell state measurement with some nonlinear interaction, you can actually make that bell state measurement into a control NOT gate. Okay, so in this way, the people found that there's a deep connection between quantum communication and then quantum computing, And then if you realize one, it's very likely you can realize the other one. Okay, and that's all for today and also for this semester. Thank you guys for spending this very I would say special semester with me, and then happy Thanksgiving, and then hopefully in the near future we can see each other in person. Okay, thank you guys.